Hello, everyone. Welcome to the lecture on artificial neural networks. So this lecture is the first lecture we're going to talk about the highly nonlinear models, which are the horsepower of a lot of amazing financial applications. Right. So let's get started. When learning something new, it's good to think about the connection with the existing knowledge we have. Right. In this case, we learned about linear regression, right? So let's just write one. The model for linear regressions, we model y as a function of the linear combination of the weights and the parameters. We have the weights, let me just write w, right? And w1 for x1 plus w2 for x2, right? And plus a noise sum. So the noise sum represents the information or the signal that we are not able to model, right? So this is something we can model. This is something we cannot model, right? So linear regression is simple because it is just essentially a linear combination of the weights and the predictors or the features. So now the connection is really if we treat the two features as nodes in the neural network, so we have nodes for x1, we have a node for x2, then they are essentially the same. So we are just rearranging the calculations, but the calculation is essentially the same, right? So this is what we call the inputs, right? Or input layer. And then we have one output. In this case, we have the targets y, or we just call y hat, because essentially this is the y hat we have, the prediction of the model. Right, so we have the input layer and we have the output layer. So in between are the weights. So let me just draw two connections. We have two weights, right? So this is for W1, this is for W2. And you may be wondering where is the W0? The W0 comes in as a BIOS term, right? This is a BIOS. So we talked about the BIOS trick before. Now, essentially, this is just add a column of ones, right? This is just one, and then make the connection. And then the weight is W0, right? So 1 times W0, right? 1 times W0. And then, so this is the different layouts, but essentially it looks like a very simple neural network, right? And we can write down the operation as, again, the same thing, but we can write in a more simpler form. So this is, we can write, for example, I equal from 1 all the way to 3, right? So we're summing from 1 to 3 the linear combination. So what is linear combination? Wi times xi, right? So for each predictor, we multiply the corresponding weight w, and then add together. So this is called linear combination, right? So this is same thing as writing y hat equals to this result, and it is essentially a linear regression model, right? So if this is the case, then building on top of this knowledge, we can add in additional transformations so that the model is more complex. Because if we do not do so, then it still remains as a linear model, which is not quite interesting and not that complex, right? So we like to add a bit of a flexibility to the model by introducing non-linearity. So this non-linearity is really something that makes the difference between linear regression and neural networks. So how do we introduce the non-linearity? We start from here. So this is the weighted sum, right? So this is a step 1. Now, step 2, I want to introduce some non-linearity so that maybe if I call this z, I introduce another variable just for notational purpose, right? So z is our intermediate, right? Our intermediate output. So with this output, I want to have another function f, and then I have the y, right? Or y hat, just different notation. So I want this model, I want this function f to be non-linear, right? So example of non-linearity is, for example, we talk about the sigmoid function, right? So the sigmoid. it maps any inputs to an output. Let me just remove this. So any inputs to a probability of okay, so I think I drew it wrong. So it should be like this. Okay. So let me just draw it properly. So the sigmoid function essentially maps input x to a probability, right? Between so this is 1, this is 0, and this curve is nonlinear, right? It's not a line; it's nonlinear. So that means we introduce some nonlinearity by using the sigmoid function, right? So in other case, we have other functions like ReLU, which we'll talk about later, right? Essentially, we want to introduce this function f so that the output y is a nonlinear function of the intermediate output z, right? So these two steps, step 1, step 2, are really the building blocks of a modern neural network, right? And we will stack a lot of these operations together. For example, we can have more than one intermediate outputs. So we have another network, right? This is Z1, this is Z2, and then they can have more layers together, stacked together, right? So this is just a fully connected neural network. Okay, so that's the connection here. So let's look at the workflow of artificial neural network in terms of the algorithm, right? So essentially, we are looking at two processes. First one is so let me just draw the input layer. So this is what we call input layer, and we may have some. So we have some nodes here, and we have nodes in the middle, right? And then we have the output. So this is called the hidden layer, right? Because they remain as the middle, they're hidden. And this is called the output layer. So when we say that's the model, the number of layers in the model, we would count from the first hidden layer. So so this is layer 1, layer 2, layer 3, layer 4. So this is a 4-layer neural network. We do not typically count the input layer as a layer, right? And then all these will be fully connected. So which means this node will be connecting to all the nodes, all the outgoing nodes, right? So and all this weights represents the weights of the model or the parameters of the model. So I keep drawing, but I just ignore the drawing here. Okay, so remember that our model framework is that this is our input data X, right? And we would go through this this whole process of calculation and its sequence of weighted sum, the summation, and the nonlinear transformations, and then stack together, right? And then gets the output y, or y hat, because it is our prediction, right? So this is called the forward pass, right? Or forward propagation, because it propagates the signal from the input to the output. And then because we still need to learn the model, right? And then we go backwards. So this is called backward propagation, backwards, right? So this backwards takes the output y hat and the y, the targets, and then calculates the loss, right? The loss is a function of the w, and then this loss then back propagates to the weights, right? So that we adjust the weights. So essentially, the goal is to find the optimum set of weights such that the loss is minimized, right? The loss is minimized. So this is the whole loop here. We've passed in the data to calculate. So pass the data to calculate the prediction, and then with the prediction, we can measure how different it is from the target. Then we have a specific measure of the deviation, which we call the cost function. And with this cost, depending on how big or small it is, then it will be sort of passed backwards to the weights, right? Through an algorithm called gradient descent or stochastic gradient descent. And then this weights will be adjusted, and then we'll have a new round of iteration with new x. Then this training continues. So this is the overall training procedure. All right, so let's look at some example nonlinear functions or activity functions and loss functions. So talk about the sigmoid, right? So sigmoid is a function that maps from my inputs to probability, right? So probability outputs, and then it looks like, for example, this is my x. Now it's my x, and then my y would be 1 over 1 plus e to the power of negative x, right? So this is the formula for the sigmoid function. It is useful for us to transform an input x to an output, probability outputs, right? So it is usually used in the last layer, the output layer of classification model, right? So classification network. Some other popular choice could be the tannage a function. So we have something like this. This is 0, right? And then it looks like y equals to 1 minus e to the power 2, and then 1 plus e to the power negative 2x, right? So this is just something that we use to express this non-linearity. There's no preference in terms of y is 2 or y is not other numbers. It's just a way to squeeze the numbers within this range, right? And the range is from 1 to negative 1. So sometimes it is useful, and sometimes, but the difference is that this region, it is really squeezing the numbers. The bigger the number, the more squeezing I have, right? And sometimes this may not be the effective ones. So a more popular choice is called ReLU, right? So rectified linear units, which looks like this. So we have this looks like this. Right? So this is 0, and then at some point, okay, so this is 0 as well. And then this is just y equals to x, right? So yeah, this range, this is y equals x, this range y equals 0, right? So in other words, it is just the max of 0 and x itself. Right? So if x is negative, then this returns me the 0. If x is positive, then this returns x, right? So which is these two cases essentially. So this becomes the most widely used activation function, because if the signal input is strong, right, it's positive, then we keep it. We do nothing with it because we want to keep it that way. But if the signal is negative, which means it's not strong, then we just set to 0. So this, for one thing, removes some input signal, because there are just too many signals, right? We by setting it to 0, we are explicitly deselecting the feature, removing the feature, right? So that's in a way plays a role of feature selection, and also reduce the number of noises, the signals. And also it's the gradient calculation is very fast, right? So this gradient is just is 1, right? Because y equals to x. Not like this region, we want to calculate the gradients, then we need to be very careful which region we are, right? In this case, everywhere, if it's along this region, then it is always 1 in terms of the gradients. So the loss function for Q is a function of W, right? So we talk about the L2 norm of some square errors. So we have the Y here, and we have the Y hat, which is a function of W, right? And then we just take the L2 norm. So this is called the sum of square errors, right? And then this is for regression, and for classification, we have the binary coarse entropy, right? So in this case, we have different y's here. This is our y, and then log for the predicted probability of y equals to 1, should denote as p, and plus 1 minus y, then log 1 minus p, right? So if, of course, this is only for one example. For many examples, then you would add the indexes here, and then add all the i's, right? So these are two commonly used loss functions when we reach the end of the fault propagation, and then these will be differentiated right? So these will be differentiated with respect to W. In this case, we are calculating the derivative or specific the partial derivative for all the W here, right? So this is something we want to calculate, or we can express this this way. So W, so we're differentiating Q with respect to W. All right. So let's look at a few illustrative examples for fault propagation. Now, this is a 3-layer network. So this is first hidden layer, second hidden layer, and output layer, right? So initially we change notation a bit. We use these two to denote the node index, right? So this is node 1, this is node 2, or feature 1 and feature 2, right? So this is essentially the features. And then we use the and then for W, because it comes a bit complex, then we need to be careful in terms of what's the index means. So this means the weight index, right? The index of the weight, and then the layers. So this looks at, oh, which layer are we? So so for example, in layer 1, we have layer 1 features here, and we have 4 connections, right? So 1, 2, 3, 4. Then we have 4 weights. So these are denoted by 1, 2, 3, 4. So these are the nodes, the weights for the indexes for the weights, right? And then coming back to the first hidden layer, let's zoom in on this one. So this is the hidden feature for the first layer, and then for the first node, right? This is what it is. And then this is the second hidden feature for the first hidden layer, right? Now, we want to look at how it's calculated. So this calculation for this feature, so we look at this guy, right? This feature, and we have 2 connections. This first connection is the second connection. The first connection gives us this one. So we take the this feature multiplied by this specific weight, right? So this is this feature multiplied by the weights, and then another feature multiplied by another weights, and then multiplied add together, and then apply the non-linearity, which is the right loop. And then we get the feature, right? So this is exactly how we would get the intermediate output for the linear regression. The only thing is we are overlaying rectified linear units, the non-linearity function. All right. So, and we can do the same for F3 as well, because there's only the one output node, so we ignore the node index here. So we have 2 connections, then we have 2 summations here, and then we have two elements here in the summation, and then ReLU, and then we get the cost function. So, which means this is our prediction, and we compare our prediction with our targets to calculate the cost, right? So it's the difference between the prediction and the target. So basically, this calculates the fault propagation. So that's actually something we are clear in terms of the calculation process. Now, when we have a cost function Q, right? Q is a function of W. Now, how do we update the weights? So the most widely used algorithm is called a stochastic gradient descent, which is defined as W, right? So if we are at iteration T, right? Iteration T. So we go by iterations. So iteration T means we currently our W is equal to WT. So this is the value of W at iteration T. And we want to get the next iteration, which is what is the W of, or what is the value of WT minus T plus 1, so the next iteration, right? So how do we change the weight so that it minimizes the loss? So we get the loss, get the value of the weights by this simple algorithm. So this is eta times the gradients of Q, the cost function, with respect to W. All right, so this is actually the WT because it is a TC iteration. So which means we take the current value of the W, right? Calculate the gradients. It can be positive, can be negative, and then multiply by the eta, which is called the learning rate. So this controls how big of the step, right? Or it can also be called the step size in each update. And then we minus it because we are descending the weights, right? So this algorithm remains the most widely used, and it gives good performance. So if we train it long enough, then it usually gives us a good generalization performance, which is good. And it was amazingly invented by in the 1950s, right? So it still remains as the most widely used algorithm to train neural networks. All right, so that's gradient descent, and let's look at specifically the backward propagation process. So once we have still the same three layer neural network, right? So this is backpropagation, and once we have the cost, then we calculate the derivative of the cost for the intermediate output f3. Now remember that we want to calculate Q with respect to W, right? But this W are all the connections, right? So these are all the connections. So this is 1W, 2W, 3, 4, right? So all the connections. So for example, if you want to calculate the derivative for this weight, then we need to go through a lot of intermediate functions. So this weight is connected to this one, and then this one, right? So this is, in other words, we are calculating the derivative of one function of one entity, right? So this entity goes through one. So this is overuse of notation. Okay, so let me use G here. So G is a function, and it is one function, right? And then go through G2 again. So this is and then go through G3, and then we have Q here. So this is called function composition. So we go through G1 first, then G2, then G3, then get to Q, right? Now I want to calculate the derivative of Q or with respect to W, right? So this is the output, this is the input. Then we want to use something called the chain rule, right? So we first calculate the derivative with respect to G3, multiply derivative with respect to, okay, so this is G3 and then G2, and then G2, G1, then multiply. So this is G1 and W. So finally it's W, right? This is called the chain rule of differentiation, right? Because of this intermediate connections, right? So it is not something we can calculate in one shot. We need to do it layer by layer to get the intermediate. This is intermediate gradients, right? So that's why we are calculating the first elements, and then so this is F3 with respect to W3, W13, and then these are the intermediate gradients, and then these are the gradients as well, and then finally we have the gradients here, right? So that's how the calculation process works, and of course, in the modern packages, all these are automatically calculated, right? So there's something called autograd, stands for automatic differentiation, right? So this it does the automatic differentiation. If you use TensorFlow or use PyTorch, then there's something that's typically done under the hood automatically for you, right? So finally, I want to bring your attention back to the overall framework we talked about earlier, right? So we start with the original data set, and then we decompose it into training and test, right? So this is our training, this is our test. So they have their different purposes. So we use training sets to train the model, right? So a model essentially is a function f parameterized by W. And then, for example, we first do prediction for training purpose, right? So we take the training data sets, apply the model itself, get the test, get the prediction, right? So there's a white hat for training sets, and then we calculate cost. The cost is a function of the training, the targets, then the prediction. So we get cost. So this cost goes back to the optimization loop, and the optimization works by the gradient descent, right? So so this is next iteration. I take the count integration values times the learning rates and then the partial derivative with respect to the W's, right? And then this optimization then goes back to adjust the model itself, specifically the weights, right? So W change, then we have a new model, then this continues, right? So this loop continues. So once we are more or less comfortable in terms of the model weights, then we can go to the test sets, right? So take the model, go to test sets, and then again, we use the model to make predictions. So this runs the predictions based on the test sets. Then we have test set performance, right? So by calculating the loss sum together, this gives our risk. So R stands for the risk or the empirical risk, right? So this is a measure of our generalization performance. So how well it generalizes to the test sets. So this is the overall framework, and I've added some notations here to make them more clearly annotated. And then again, this is from my book Regularization Deep Learning. So again, if you're interested and you want to read out more, feel free to check out the book. And otherwise, I will see you next time. Thank you.